in previous classes, we were discussing about various types of interactions and their distance dependence. Ion-ion interactions, ion dipole, dipole, induced dipole, etc., etc. Okay. So these interactions are actually important because protein side chains, you have all varieties of side chains. Aditya, recording, right? Aditya, are you there? Okay, you are recording. Okay. So, so today we'll discuss about other important interactions which dictate protein structure. Okay, so this revolves around water. So we need to discuss about water and solubility of compounds in water, because when we talk about proteins, mainly we are talking about physiological conditions. So physiological conditions means that you have a buffer, typically phosphate-based buffer conditions, pH 7.4, and this buffer means that it's basically solvent is mainly water. So we are going to discuss about the folding and structure of proteins in water. So water, it's basically a triatomic molecule consisting of two hydrogens and oxygen, and it's basically bond length and bond length. Bond angles and bond lengths roughly about 105 degrees, and it's about, bond length roughly about maybe 1.3 angstrom. Okay, and the important property of water is that, so because the hydrogens are attached to an electronegative atom, so these hydrogens can form a hydrogen bonding. Okay, or hydrogen bonds with other electronegative atoms like nitrogen or oxygen coming from other molecules. So that's an important property of water molecule, mainly involving hydrogen bonding, either by donating hydrogen or accepting hydrogen from other molecules where hydrogen is attached to again electronegative atom, right? So that's the property of a water molecule. And water by itself in solvent, hydrogen bonded to other water molecules through hydrogen bonding through other hydrogens from other water molecules and donating hydrogen to other water molecules to oxygen. Okay, so this is a very important property which distinguishes water as a solvent from any other solvent. Okay, so if you take any compound and try to dissolve in water, okay, so you can classify compounds into different types. Let's say ionic compounds. For example, let's say sodium chloride. Okay, so if you take a pinch of sodium chloride and put it in water, so this will be dissolved into sodium plus and so chloride minus, right? And then because now sodium chloride is a solid when you put it into solvent water, so they are dissociated because so these dissociated ions are stabilized by water molecules. Okay, so water molecules, because water is a polar and also dielectric, so that it can actually screen charges of coming from, for example, let's say it screens the charges between sodium ions and chloride ions so that they're far away from each other, so that they're surrounded by water molecules. Both sodium and chloride are surrounded by, okay, so water molecule, so that this compound is actually in the end is dissolved. Okay, so this is one of the property. So where, because you have charged ions, so which are actually screened from other charges because of this dipolar nature. So this is an important property of water. So ionic compounds can be easily dissolved in water by this process because the stabilization energy is coming, because the solvated ions have lesser energy than the whole compound. And you can have compounds where hydrogen bond forming compounds. Hydrogen bond forming compounds. Okay, so there are plenty, but let's say you take function groups which are relevant to proteins or amino acids. You can have amines, alcohols, ketones, etc. Okay, ketones, aldehydes, esters, etc. So all these groups, all these functional groups have electronegative atoms like nitrogen, okay, oxygen. So these electronegative atoms actually can form hydrogen bond with the water molecules. So thereby they get dissolved. Okay. So two hydrogen bonds. Let's see if it is amine. Okay, so let's say you have two amines. So these hydrogens can be bonded to OH2. Okay. So So similarly, like ketones and aldehydes, they have oxygen groups which can actually form hydrogen bonds. So ionic compounds get dissolved because of the charges are screened by dipolar nature of water molecules and the dielectric constant, which can really screen hydrogen bonding compounds like amines, alcohols, etc. So it's easy to understand these kind of functional groups which can be dissolved in water. Okay, but what about non-polar? Okay, non-charged are basically which don't have charge. Okay, compounds. Okay, so for example, let's say simple molecule like methane. Okay, CH4. Okay, CH4. The question is that does it dissolve? Okay. So all the above compounds we call hydrophilic because they like water or dissolve in water. Okay. Okay. So, but what about non-polar, non-charged compounds? Do they dissolve in water? Okay. Any takers?
They will not be dissolved in water.
They will not be dissolved.
Okay. They dissolve in water?
No, sir, they will not be dissolved.
They don't know.
Okay. I heard just an answer, I think, before someone said that it dissolves in water. And then I also heard an answer where it says someone said that they dissolve in water. Okay, so two conflicting statements have been made. So which one is correct? Or both are correct or both are wrong? Okay, so let's say people who said that it's not the, for example, let's say methane doesn't dissolve in water. Okay, why do you guys say it does not dissolve in water? Or water does not dissolve? Methane? Hello?
Methane will not be dissolved in water.
Can you speak a little louder? Who is this?
Methane will not be dissolved in water. It's
Okay, methane
completely
does not
hydrophobic.
dissolve in water. Why? Why do you say that?
Sir, here the hydrogen is attached to the carbon atom, which is not much more negative. So the partial positive charge on hydrogen is much more less to form a hydrogen bond with the water. So no such kind of interactions will prevail in the water if methane molecule is try to dissolve in the water. So that cannot be stabilized in this water.
Okay, so you say basically it's not dissolve, it doesn't dissolve in water. Okay, so people who said it does dissolve in water, what do you guys say? Anyone said that it gets dissolved in water? I heard the answer, both arguments. Okay, it's a discussion, don't worry. It's
Sir, I think no one has said that.
no one has said that. Okay. Okay. So so you're saying that it doesn't dissolve at all. Okay. So we need to be very careful. So sometimes you don't have a simple answer like yes and no. Okay. So sometimes you need to get to numbers, to say instead of saying yes or no or true or false. So let's say if you compare methane with, let's say, sodium chloride. So then sodium chloride, you can really put a lot compared to methane gets dissolved. But methane also gets dissolved, but only thing is that not as much as you would like it to be as sodium chloride. Okay, so that's the only difference. Okay, so but instead of talking about the numbers, because the solubility is very low, or sometimes we call, what do you call, sparingly soluble. Okay, so what's the meaning of sparingly soluble?
Their solubility product is very much low in the sparingly soluble salts we get.
Yeah, so it's very low. Means that you can't really put a lot of compound in a solvent and then make it a solution. Okay, so that's what is sparingly soluble. So it's the same thing with methane. So you can't really put a lot of methane and you say that okay, it's a methane water solution. But any compound, if you take, it's soluble, maybe very low. It's the same thing with methane, So methane can be soluble, but it's so low that typically you want to just call it, it's not soluble. Okay. So what happens if you put it in, try to force? Okay. So methane is a liquid or gas or solid? Let's say physiological conditions.
Gas.
Gas.
Not STP conditions, not physiological, STP conditions.
It's a
Gas.
Is
gas.
it a gas or a solid or liquid?
It's a
Gas.
It's a
gas.
gas.
It's a gas. Okay, very good. So let's say if you take a water and then let's say if you bubble methane into that. So what will happen? Basically, you're forcing, right? Okay, so you don't think that not even few molecules of methane will go into water?
Yes, sir, they can go through van der Waal interaction as
Okay,
water
so
molecules.
obviously you're really forcing, right, the gas. Okay, and you're forcing the gas pumping the gas into water solvent, and a lot of gas is not dissolved like oxygen or any other gas. Let's say, for example, hydrogen bond forming gas, where more molecules relatively go into water and get solvated. But methane, of course, that number is very low. But nevertheless, you can always find molecules, okay, methane, which are dissolved. But the thing is that, so what will happen? Let's say if you have to imagine an isolated methane molecule in water as a solvent, okay? So then, so what will happen? Let's say if you put, let's say hydrogen bond forming molecule, let's say a small amine, okay? So simple amine, let's say lysine. Okay, so if you try to put lysine, so then lysine nicely go into solution, and then you have amine groups. So you have NH2. So these NH2 nicely form hydrogen bond with water molecule. So water molecules to begin with, they have kind of in the ice you have perfect tetrahedral structures. Okay, so coming back to water. Okay, so ice, so you have tetrahedral structure. We call lattice. So where you have a water molecule which perfectly forms, okay, hydrogen. Let's see. Okay, so oxygen forms two accepts two hydrogens from neighboring water molecules and it donates. So at any point of time, you have a water molecule which is exactly having how many hydrogen bonds?
4 hydrogen bonds.
4 hydrogen bonds.
4 hydrogens. Okay, so through two hydrogen bonds through donation, 2 hydrogen bonds to accepting hydrogen as accepted. Okay, so this is perfect tetrahedral lattice. But however, if you melt the ice into water, okay, so on an average now these hydrogen bonds are not fixed in water. Okay, unlike in ice, so these are not permanent or fixed. In ice, as long as ice is not melting, they are fixed. So in water, so liquid water, so these 4 hydrogen bonds, okay, what you call breaking and forming, okay, they continuously break and then form, okay, or sometimes we call fleeting. So fleeting hydrogen bonds, but on an average again water will have 4 hydrogen bonds. But only thing is that they are not really fixed. So sometimes it forms with neighbor, sometimes it forms with other neighbor, and sometimes water molecules, okay, mobile are moved, okay, with respect to each other, so that during this breakage, okay. But on an average, you have 4 hydrogen bonds. So this is a stable structure for water molecule. So any point of time, if your water molecule has 4 hydrogen bonds, it's nice and happy. So when you put hydrophilic compounds, okay, so now they need to dissolve. Okay, so once they are dissolved, so they are surrounded by water molecules, and these water molecules actually now, instead of forming a hydrogen bond with its neighbor, so you can actually replace this with a solute. Okay, so hydrogen bond donating solute, so that you have hydrogen bonds are satisfied in the end. So it's not a problem for hydrogen bond forming solids. But if you put a methane, okay, so it's surrounded by water, and imagine the water molecules on the surface of, okay, on the surface of methane molecule. Okay, so any atoms which are actually facing towards the methane surface have no way to form hydrogen bonds. Unlike in hydrophilic compounds, okay, or hydrogen bond form compounds, they can actually donate a hydrogen bond so that they are, on an average, 4 hydrogen bonds are satisfied. But if you have a compound like methane, okay, so which we call hydrophobic. Okay, hydrophobic compound. Okay, so we are talking about very sparingly soluble, very few molecules. So now these atoms which are close to the surface of methane molecule have no way to form hydrogen bond. So they have to really satisfy their hydrogen bonds only by reorienting or maximizing their ability to form hydrogen bonds. So it's true for all water molecules which are on the surface of methane. Okay. So now, so they cannot really have a tetrahedral lattice. Okay. So tetrahedral lattice is perfect for water molecule to exactly have two hydrogen acting to act as two hydrogen bond donors and act as two hydrogen bond acceptors. But then there is a problem when you have a hydrophobic compound. So then the structure around the surface of this molecule, or let's say if you call the hydration shell. Okay, so the molecules which are just surrounding the surface of this molecule called hydration shell. Okay, so this hydration shell structure is different whether it is a hydrophobic compound or hydrophilic compound. So hydrophilic compound is easy to understand. So the shell is just like as if few water molecules just missing in the at the center. So the shell still have kind of tetrahedral structure. But the hydrophobic molecules, the shell looks like, I'm going to show. Okay, so I need to share the screen. Okay, you guys see my screen?
Yes, yes.
Okay, not this. Yeah. Okay, so everyone sees my screen. Okay, so this is so this is a pictorial representation of what it might look like if you take a methane molecule CH4 and then put it in water. Okay, so the water forms what is called a cage-like structure where the water molecules on the surface form a kind of structure, okay, where each water molecule is trying to maximize the number of hydrogen bonds it can actually make. So these structures are often called clathrates, okay, or if they are made up of water, these are like water cages. So these structures are different if you have a hydrophilic molecule at the center. So then these structures will just look like tetrahedral structures of ice lattice. Okay, so this is possible for hydrophobic molecules. Okay, so now, so this is, if you think now, so these water molecules, so need to have a specific structure on the surface. Okay, so these are really ordered structures. Okay, so these are ordered than regular ordered, let's say tetrahedral structures, is because in the liquid water, though you have on an average 4 hydrogen bonds, so these hydrogen bonds are actually breaking and forming. So you can always have break a 1 hydrogen bond, a new water molecule is going to come, satisfy that. Or you have a hydrogen bond donor or acceptor, which is going to satisfy. So that's why it's fleeting structure, because it's a liquid, it's not ice.
Sir, I have a question.
But on the other hand, if you have a methane molecule, so you can't have a fleeting structure because you can't really assume, you can't really expect a water molecule which is far away from the surface to come and exactly satisfy. So this is a kind of a rigid structure and rigid, I would say a rigid, okay, ordered structure, making it, okay, kind of permanent. Okay, so this is not a fleeting structure like in liquid form. So because of this, so now you have to really think about what will happen to entropy of this structure. Okay,
Sir, I have a question.
so yes.
So, sir, when we are considering the solvation of ions, so how do the tetrahedral structure of water molecule is being maintained there?
Okay, so if you talk about the ions, okay, so again you talk about the size as well. Okay,
Yes.
First of all, these sizes are not really big. Okay, so second thing is that there are charges there. Okay, so still water molecules can reorient such that they can actually satisfy, let's say, 4 out of 3 hydrogen bonds. And the third one is actually stabilizing the charges. Okay, so you have a sodium positive charge and you have oxygen, let's say partial negative charge. that is actually more stabilizing. Okay, so than hydrogen bond. And at the same time, water molecule can have other hydrogen bonds. And third thing is that water molecule can reorient. Okay, so there are a lot of features which make them stable structures if you put ions. But here we are talking about first thing, slightly larger entity. So if you compare, let's say, a methane, we are talking about the smallest, organic molecule, but typically organic molecules are larger. Let's say if you talk about a lipid molecule, okay?
Yes.
So you have a side chain of anywhere from 10 to 20 atom carbon chain, okay? So this is methane is the simplest. So next complex thing is ethane, okay? Next is, let's say, propane. So these are much larger. Okay, so then the effects we are talking about, the ordered nature of the water shell around these hydrophobic molecules is basically much larger. Okay, so you can't really, okay, in other words, let's say if you have to put a hydrophobic molecule. Okay, so let's say this is basically polymer of, let's say, carbon. Okay, CH2, CH2, CH2. So now all this surface. Okay, so I have put only 2-dimensional, but you can really think about 3-dimensional. Now all the water molecules, okay, on this are basically used surface area. Okay, so here they need to be really perfectly ordered. So all this shell, okay, much larger compared to water molecules surrounding a small ion like, let's say, sodium or chloride, where so these individual molecules can actually rotate, but here they cannot really rotate. So they have to really try to optimize their geometry such that on an average they have more hydrogen bonds. Second thing is because they cannot really make any strong interactions in terms of hydrogen bonding or dipole interaction, because these are non-polar molecules, you know. So all those interactions are actually completely absent, but these interactions are actually present if you talk about ionic molecules or hydrogen.
Okay, sir. Okay, sir. Okay, sir.
Okay. Okay. So we have to really think about now entropy, because the moment we talk about order structure, so we have to really talk about entropy. So what will happen to the entropy of water now? Patrick, okay. So what will happen to the entropy of water on the surface of this?
It will decrease.
It will pretty much be reduced entropy.
Okay, so entropy actually decreases, right? Because it's ordered. Okay, so entropy decreases, right? Sorry, what? So I think here they are having. Okay, so they are showing 1, 2, 3, 4, 5. Okay, so there are 5 methane molecules. Okay, so each is forming a shell. Okay, surrounded by water molecules. So these water molecules are actually highly ordered. Okay. Oh yeah. So again, here also, so these. I don't think you have exactly the structure. So most of the data actually come from simulations. Okay, so you put a water molecule, you minimize water box, you embed literally a methane, and then you minimize. And then what you can actually get is, you can interestingly calculate, I'll forward, there is a paper. So you can actually calculate from the center of methane, okay, as you go radially anywhere. So you can actually calculate what is the number of water molecules. Okay, so you get beautiful fine structure, beautiful, let's say, okay, distance from center of, okay, distance from methane center. Okay, so at the center, of course, you won't have anything, but then it just peaks, means that there are a lot of water molecules at exactly a fixed distance, and then that actually goes down. Okay, and then you get a second peak, and then basically, okay, so what do you think is this value? So what are we plotting? Distance from CH4, let's say water density. Okay, so we need to, not the number of water molecules. Number of molecules are always large, larger sphere, right? So density. Density of water. Okay, so initially it's 0 at center. There is a maximum, and then second. So this is actually first shell, second shell, third onward, and this is actually bulk density. Bulk density. That's basically bulk water density. So, but you see, this is much higher than the bulk water density. Means that now the water molecules arrange themselves such that the density is higher, but again a fixed structure. So that's what actually they're showing the first shell. So you can have analogously second shell, but second shell density is slightly lower than this, but then third onwards this. Okay, so this shows that again, see, this is lower than this is higher than this. Means that you won't find a water molecule at a certain distance because there is a shell before that is fixed. Okay, so what is your question then? How exactly the arrangement? So the arrangement comes only from the simulations. Okay, so but here actually they are showing more than cluster. So these clathrates again clustered together, but you can think about individual clusters. Okay, so now as you guys pointed out, so the entropy of water decreases, right? Okay, so the entropy of water decreases because of the ordered structure, right? Okay, so now, so we have to apply this concept. Okay, so entropy decreases means that this is not a stable structure, right? So that's why what happens is that if you put a methane molecule forcibly into water, so now let's say imagine if there is another methane molecule in the neighborhood. Okay, so this also has the same problems. Okay, so the treatment is exactly same. But now imagine you bring these two methane clathrates, okay, methane water clathrates. So now, so when you have individually, you have a certain number of water molecules proportional to the surface area of methane, which are actually ordered at different methanes. But now if you bring in these two close to each other, so what will happen? So then basically imagine this is the surface is going to be overlap this. So now, so this methane will interact with each other. Now the surface area per methane molecule, okay, which needs to be covered by water reduces. Means that the total area is now less than the sum of the areas. Okay, so that you have now less number of water molecules which need to be ordered. Now you can actually argue, let's see if you have similar third, okay, methane water cluster, which you brought into this. Okay, so now the average, the area per methane molecule is less, and so you have less number of water molecules. So basically now this drives, okay, so to clustering now methanes come together and form a single entity so that you have to deal with less number of water molecules which need to be ordered. Okay, so in that sense now the entropy decrease, okay, is less and less when you have either a large, okay, large surface area versus the same surface area is divided into few distinct, okay, non-overlapping pieces. Okay, so now this says that, so it's good to have, if you have many hydrophobic surfaces in water, So it's good to have that you combine all these hydrophobic, okay, volumes into single entity, so that you have the surface area is actually lessened or minimized, so that your water ordered problem will be reduced rather than having individual pieces. Okay, so this is what exactly happens in proteins. Okay, so in proteins, what happens is that, let's say if you have a side chain, okay, C alpha, CO, NH, okay, so then C alpha, etc. Okay, so let's say you have a phenylalanine. Okay, so let's say if you have a tryptophan, so let's say if you have an isoleucine. Okay, so these are hydrophobic groups. Okay, so these are hydrophobic groups, just like the methane we dealt with. Imagine now a polypeptide chain which is dissolved in water, and these individual side chains are exposed to water, forming, imagine a clathrin. Okay. Okay, so this is exactly like what we dealt with. This is like a methane example, another methane example, another methane example. So what did we discuss there? So if you bring all the hydrophobic side chains as a cluster, so then the total area is also minimized, and then so that you have less and less water molecules which need to be clustered, right? So this is what really happens if you put a polypeptide chain consisting of basically all kind of side chains. Then especially the hydrophobic groups, okay, so around which water is having a ordered structure, having less entropy. So now combine, so that now water, this ordered water will be released. So once the ordered water will be released, so these water molecules have freedom to reorient and get to their bulk water-like structures. Okay, so there is a change in the entropy. So the entropy is actually favorable. So this is the less entropy if in the clatrate form, but this is, the entropy will get released if you have this thing. So we have to really talk about entropy change. Okay, so from the water. Okay, so what happens delta S? So delta S is negative or positive? So water to begin with forming a clatrate structure. So now in the folded protein, so these hydrophobic groups, for example, let's say tryptophan, phenylalanine, let's say isoleucine, forming, okay, C double bond NH. Okay, I'm just writing a carbon structure. Okay, so now you have, okay, groups, okay. So you are taking a polypeptide chain where hydrophobic groups are exposed to water, forming individual clatrate-like structures, ordered structures, where entropy of water is very low. Okay, unfolding, you bring all these hydrophobic groups clustered together so that you have less surface area. And so this process is called hydrophobic collapse. Okay, so this process of bringing all the hydrophobic groups in a polypeptide chain to clump together, okay, is called hydrophobic collapse. Okay, so in this process, what's happening? You have to think about from different chemical entities perspective. First, water. Okay, so entropy change of water. So entropy of water is actually increasing or decreasing in this process.
Increases in this process.
Sorry.
Increases in this process.
Okay, entropy increases. So is it a favorable process or not?
Thermodynamically favorable.
Okay, can you guys repeat that again?
Thermodynamically favorable process it is.
Okay, so it's a favorable process, right? But if you think about from the protein point of view or polypeptide point of view, so which one is more ordered, the unfolded chain or the collapsed chain?
The folded is more ordered.
Folded is more order.
Okay, so entropy change for so I will write a peptide. Okay. So for this, delta is increases or decreases?
Decreases.
Decreases.
Decreases. Okay, so water likes obviously because now it doesn't have to be ordered. But however, polypeptide says that okay, I have more freedom in unfolded state, but in the collapsed state, my entropy is actually decreasing. Okay, so at the same time, what's happening? The interactions between okay, so what kind of interactions are between these kind of side chains, which we discussed, like ionic dipole, dipole-induced dipole, what kind of interactions, for example, between, let's say, tryptophan, phenylalanine, isoleucine.
So Van der Waals type of interactions can be there.
Sorry, again?
The Van der Waals kind of interactions can be there. On the tyrosine molecule, there is a OH, and in the leucine, there is a NH2 group. So this can form also hydrogen bonding between them, the residues. So
hydrogen bonding.
Tyrosine has the OH, the phenol group. Tyrosine has.
Tyrosine is not there. We have only tryptophan, phenylalanine, and isoleucine. All three are hydrophobic groups.
Yes.
There are no OH there. Okay, so Van der Waals interactions are basically dispersion, induced dipole, induced dipole.
Dispersion, induced dipole.
Okay, so those are stabilizing, right? Because to begin with, they don't have any interaction. So you brought together those interactions. Okay, so side chain interactions are stabilizing. Okay, so increases. So this is stabilizing. So this is destabilizing. Right, because entropy decreases, it's not a favorable process. But the side chain interactions, let's say I put Van der Waals interactions, is actually stabilizing. Huh?
Is protein entropy method?
Oh yeah.
Because if I consider the isoleucine for the tryptophan as a bead, not as individual item, but as a bead as a whole. And once you are clapped around them, it's a fixed structure, right?
Yeah.
So this bead is more or less long. So should it be like, so is there one configuration? Yes, so there is only one microscope when it's open.
Yeah.
There is only one microscope when it's closed.
Yeah, so but we are actually indirectly we are talking about the freedom along this chain as well. So right, so the moment you are actually bringing these two, so the freedom along this chain is basically affected the conformational freedom. Okay, so it's basically the entire polypeptide. Okay, so that's a very important point. So yes, entropy of the polypeptide is very important. Okay, so now we discussed about basically three terms. One, so let me put it this van der Waals interactions as enthalpy. Okay, so enthalpy contribution. Okay, so now let's say if you want to know that entire folding, okay, so the folding of a polypeptide chain from not in native state to, let's say, folded state, okay, folding. Okay, so basically now, so in the protein folding, so one is to really, it shows that you cannot really ignore just solvent per se. You can't really just think about only peptide and their interactions and its entropy, but you have to actually factor in the entropy, okay, increase in the water. So though the entropy of the peptide is actually decreasing, because so typically we say that okay, anything entropy increases is typically favorable because the disorderedness actually increases, right? But in the case of protein folding, it's opposite. So you have a disordered peptide going to have well-defined ordered structures. So obviously entropy is actually decreasing, but it extends. So you have van der Waals interactions. So van der Waals actual interaction are stabilizing. Okay. So now we have to really think about, let's say, if you want to know the free energy, okay, total free energy, energy change, okay. So that's what actually dictates in the end whether a protein is folding or not. Okay. For most of the large proteins which have a mixture of hydrophobic side chains, hydrophobic side chains, etc. So most of them actually in the cell go to a native state. So that's why actually we are living, because proteins are really functional. Okay. So let's say then in that case delta G needs to be negative because it's a spontaneously, okay, so free energy change, proteins folding spontaneously. Okay, so we are not really talking about nitty-gritty details of chaperones misfolding or not, but let's say they fold, most of the proteins actually fold very nicely to their native state. Means that they are spontaneous process, so delta G negative. Okay, so now, so we have three contributions to the delta G. One, the stabilizing forces or the enthalpic contribution that mainly comes from side chain interactions. And also now if you club your hydrogen bond forming, for example, let's say when we said that if a polypeptide chain forms a alpha helix, okay, so then we know exactly where the hydrogen bonds. Let's say if it forms a 310 helix, we know where the hydrogen bond. Let's say if it forms a beta sheet or antiparallel beta sheet, we know where the hydrogen bonding between. So all these are enthalpic contributions. Basically, any of those interactions are actually forming. It's a stabilizing because it stabilizes this. So all those actually come under now enthalpic contributions in addition to the van der Waals interactions between the non-polar side chain. Okay, so that's basically a delta H. Okay, so a delta H, okay, enthalpy. Okay, so this is basically stabilizing. So if it is a stabilizing, delta H is negative, right? Okay. So then delta S contribution is from two, one from the peptide, one from the water. Okay. So from the water, so finally what is important is actually T delta S. Okay. So minus T delta S is what actually we calculate. Let's say from water perspective. So what is minus T delta S sign? Okay, in the end.
Negative.
Negative, right?
Yes.
Yeah.
So this is also stabilizing because it makes delta G minus minus. So the third contribution is T delta S coming from peptide or protein. Okay. So minus T delta S value of peptide is going to be, because delta S is actually decreases, so T delta S is positive. Okay. So now, so your protein is going to be folded if the sum of these three terms is negative. Okay. So delta H is typically negative, but these two are actually dictating in the end. You know how much actually the peptide is actually, so entropy is decreasing, so that's why it's positive, but at the expense water actually being released, so which is actually bonded to the peptide now has freedom, so that will be negative. So the balance between these two more or less actually dictates whether a given polypeptide chain will go to a folded state or not. Okay, so I'll give you some example numbers so that you will appreciate what are the values. So in a pictorially, so one can actually represent, let's say the sign. Okay, so let's say, so if you have to do this, okay, so that's your 0. Okay, and let's say this is positive and this is negative. So your T delta S, okay, T delta S of peptide. Okay, so sometimes you can actually write this is conformation of entropy, and this is because we are talking about water, so this is sometimes called hydrophobic effect. Okay. Okay. So this is T delta S of conformation. Okay, so that's positive contribution, and your delta H, so that's negative, and then your T delta S, T delta S. Okay, so this is hydrophobic. Okay, so these two together, okay, unless they outweigh this, your protein is not going to be folded. So this is basically the essence in terms of energetics. Okay, so I'll give you a small table and numbers so that you appreciate that how individual numbers are so high, but yet delta G values, okay, are much smaller compared to this. Okay, so ribonuclease, a protein. So people have estimated for this. Okay, so delta G of folding, delta H, and delta S. So delta S, okay, so units are important. Per minute, yeah. So the delta S is minus 774. Delta G is used very big, minus 238 kilojoule per mole. But yet, if it is use a delta G, it's only 7.3. Okay, so this for this protein, ribonuclease. So if you see the delta H minus 238 kilojoule per mole, it's a very large value. Means that you have so many functional groups. When they interact with each other, they provide so much enthalpic stabilization. Huge value. But however, so though this is very huge, but these two values are actually equally important. Okay, shows that in the end, your delta G is such a small fraction compared to this. It's only minus 7.3. Okay, so minus 7.3 kilojoule per mole. So units are same. See, this is in hundreds. This is not even close to 10. Means that so most of the thing, okay, destabilization is actually coming from this TPS. So that's why though this is very large value, because of this is also large, the sum of these two will be smaller. So delta S, I think they have given put together. Okay, so that will be again, this is also large value, minus 774. So this they are writing only for folding. Okay. Okay, so I'm not sure how exactly to, but anyway, so units are different. So it's joules per degree per mole. So this is joules. So if you convert this to kilojoules, so it's only 0.7.
0.7 into plus 300 Kelvin.
Exactly. So 300 Kelvin. Okay. So, but in the end, what's important is that so delta G values are typically much smaller than individual delta H and delta S. But however, that small difference in the end will dictate. Imagine this is slightly larger, so then this will be very close to zero, then the proteins will not fold. Okay, such small in the end difference, okay, very small negative value is going to actually drive the folding. So the first step in folding is basically the hydrophobic collapse. Okay, so where you have a large polypeptide chain where you have all the functional groups come together, especially the hydrophobic groups, because, for example, like methane example, if you try to pump methane into water, so it's very sparingly soluble, but however, it wants to combine with a neighboring methane molecule so that it can actually form cluster. So this is one of the driving forces for formation of membranes. Okay, so if you put lipid in water, why it actually forms a double layered structure, or if you put a surfactant in water, why it forms a micellide structure is because it wants to really get rid of water. Okay, because water also wants to get rid of these molecules so that they can form fleeting hydrogen bond structures with themselves. But at the same time, these molecules want to interact with same kind so that they form cluster. So this is a main driving force for protein folding as well, where all the non-polar structures come together, form a cluster, okay, in the process called collapse or hydrophobic collapse. So for which the driving forces are basically one, the entropy stabilization, okay, coming from water release, okay, at the expense of order structure of the polypeptide chain. But however, because the interactions between the non-polar groups, the delta G is also stabilized. So this is the first step, the collapse. But then after the protein is actually collapsed, so now the finer refinement will come into picture. The groups which form, let's say, salt bridges, the groups which form hydrogen bonds will come into picture, will dictate the finer structure of the protein, okay, so that it will have a well-defined native geometry. But let's say if you don't have these hydrogen bond forming groups or salt bridge forming groups, so then again the structure is actually collapsed globule, but then this globule can change its local structure because van der Waals interactions are actually not directional. Hydrogen bond interactions are directional. Charge-charge interactions are directional. Van der Waals interactions are not directional. Okay. So if you want to have a finer structure for protein, so first thing is that you need to form a collapsed structure, and then you refine, okay, your relative orientation of the functional group, so that you have well-defined structure in the end, where we really talk about secondary structural elements organized with respect to each other, giving okay tertiary structure. Okay, so that actually completes the kind of interactions which are involved at the molecular level or the functional group level, which actually dictate, okay, what structure a polypeptide molecules would take. So next class onwards, we'll discuss about kinetics of helix formation and then initiation, etc. Okay.
Sir,
Sir, I have
So
a
that's
I
all
have
few
for
questions.
yeah. Ready for I can address questions.
Sir, in these cases, we are dealing with the delta G, delta H, and delta S values, which are all dealing with the thermodynamics. So
Yes.
this tells us is the reaction is spontaneous or not. So
Correct.
how can we get the kinetic information that this should cross a potential energy barrier na, for folding?
Exactly. So far I have not really discussed about the barriers. Okay. So I discussed about basically overall stability of structures. So purely you're right. We talked about only the thermodynamics. In the end, the structure is stable or not. So yeah, this does not tell anything about the kinetics. The kinetics one needs to really deal with a different way.
Sir, so then how to measure this activation energy barrier for this folding
No,
process?
no. So then one needs to really, so when I said the collapse,
Yes, sir.
okay. So how fast is the collapse? That is dictated by the kinetics, the rate at which the collapse forms. And after collapse, how exactly the structure might be evolving. So all these things involve kinetics, but that does not really dictate the delta G.
Yes,
Okay.
sir.
Okay. So kinetics either independently one needs to measure.
Okay, sir. Okay, sir.
Okay, so in other words, you can have two systems where the stabilization might be exactly same, but however, in one case, the rate might be faster because the barrier is lower. In another
Yes,
case,
sir.
barrier might be higher, but however, despite the rate is low, in the end, the overall stabilization or the thermodynamic stability is exactly same. Yeah, kinetics is totally different from this. So we haven't really talked about barriers. We will talk about them when we do the kinetics. Okay.
Okay, sir.
Yeah. Another
Sir, I have
question?
questions. Yes, sir. So how do we calculate these thermodynamic parameters like delta G, delta H, and delta S? Because temperature changes won't be that appreciable. So
Yeah. So there are actually plenty of methods actually to calculate the overall thermodynamic stability, delta G values. Okay. So it's easy to measure the overall change, but rather than dissecting them into delta G and delta S. Okay. So very simple methods are, let's say you can actually take a protein which goes from folded to denatured state, and then you can actually do the you can calculate directly either enthalpic changes. There are calorimetric methods which are direct. So you can actually measure the change in the heat changes. Okay. So then you can actually convert that into delta G. There are direct methods and there are indirect methods. So typically indirect methods are sometimes easier to use, like efflorescence or absorbance or circular dichroism. You can actually measure the concentrations. Okay, so by measuring the concentrations, by perturbing them using either temperature or the denaturant, then you can actually extrapolate and then get at room temperature what is the delta G.
okay, sir. And so the next question is adding iron to the water, in which we have the peptide chain. Does it changes the folding of the peptide chains?
Are you saying if you add ions?
Yes, ions like sodium
Yeah.
or something.
So, yes. So ions will have effect because so mainly their effect will be in the case of formation of, for example, let's say salt bridges, or even influencing hydrogen bond. Okay, so if you have like sodium chloride, okay, so if you put it in water, what will happen? Because it will break, because water actually able to screen charges of one type of ion from the other. Okay, so water has this because of the high dielectric constant. So now let's see if you put more and more salt into water. So now this salt can actually screen charges between side chains in the same molecule. If they're able to screen the charges, then in the end you won't have the interaction. For example, let's say there is a salt bridge between lysine and let's say aspartic acid. So now if you put more and more salt, because the salt bridge, let's say if it is on the surface, so it's screened by the additional salt solutes. So salt has some effect on this, yes.
Okay. And sir, I have one more question. It's regarding cryo-EM. When we are performing cryo-EM onto the protein samples, then we add surfactants because the protein molecules at the at the surface will have different conformations due to the air-water interface. So how does that interface affects the protein conformations?
Yeah, so yeah, typically we talk about molecules which are surrounded by the solute, surrounded by the solvent and ions. Yes, but let's say if you have protein molecules, okay, extreme thing, let's say in a dry state, okay. So then the structure might be slightly different because now you don't have intervening solvent molecules, so that so then because there is no solvent screening, so the side chain functional groups might be colliding with each other, collapsing. Okay, but let's say if it is a globular molecule, okay, so but you have a density of atoms, so you can't really pack much more closer than that. Okay, so then if the side chains on the surface which are actually projecting outside and the core is really dense enough, you can't really collapse enough. But the side chains on the surface, if they can reorient, because the absence of solvent and the salt, they can actually form nice salt bridges and things like that. But the same molecule, if you put it in, let's say, water containing little bit of amount of salt, so now the salt can actually bridge these two groups. Okay, so in that sense, the molecules at the interface, where their partial surfaces are actually exposed to what? Exposed to, let's say, air. Okay, so then you won't have that intervening salt molecules or solvent molecules. So then the functional groups might, if they're oppositely charged, they're stabilizing. But if they're same charges, because the screening is absent, they are repelling. So depending on what charges in the neighborhood, it could be stabilizing or destabilizing on the surface of the water molecules. So definitely they'll have some effect. So, but how people actually make, when they make protein samples in the solid state, there are many different methods. Okay, for example, let's say slow removal of solvent versus freezing the structure and then removing the salt. So if you try to remove the solvent slowly, then whatever all the effects we talked about come into picture, because the protein molecules have enough time to respond to the environment and respond with respect to their neighboring functional groups. But there are methods where actually you freeze the structure, means that you take the protein solution, put it in liquid nitrogen. So it's basically flash freeze. So basically both the solvent and the solute are actually frozen in whatever conformation they are. Now, if you try to apply vacuum and then evaporate the solvent, so people believe that this conformation is exactly preserved protein molecules because they don't evaporate. Only the solvent molecules actually evaporate. In the end, you have protein structure as in water, a solution, but without solvent molecules. Okay, so but there might be long-term consequences because because there is nothing on the surface of the protein molecule. Again, these functional groups can locally adjust themselves to minimize the interaction. So yes, the protein molecules especially on the interface. It could be air water, or it could be water, other solvent. Okay, sometimes it could be organic solvent, or completely lyophilized samples where actually you don't have any liquid. So the structures could be different, so it's still debatable, but sometimes people actually try to believe that the structures are actually not portable. These are questions are still haven't been completely addressed in research field, but people make sometimes assumptions so that they can actually understand or interpret their experimental results. Okay, but there are different ways of actually making samples. So if you flash freeze, then protein conformation is preserved, that I can say.
Okay, but sir, if the sample is frozen, then what is the benefit of adding surfactant to it?
No, surfactant, no. So it's not that surfactant is added to all samples. So maybe typically
Okay,
you add
it's optional
not,
whether to use it or not.
No, it's not necessary that all protein samples need to be have. But let's say if you are working with a protein which is at the interface, let's say partly embedded in membrane, let's say partly it's exposed, So then part of the surface which is actually embedded in membrane needs an non-polar environment or a membrane-like environment. So in those cases, you can actually add a little bit of surfactant so that the interactions of that part of the protein are compensated by your surfactants. But it's not that all soluble proteins need to be interacted with surfactant.
Okay.
But yeah, even if you have small amounts of surfactants, they might actually solubilize proteins. These are like detergents. They might actually denature. Yeah, one needs to be very, very careful. So if you add, let me put it like this: if you have a completely soluble protein, and then if you add very tiny amount of surfactant, actually you will be affecting protein structure because it might be poking into protein structure, individual surfactant molecules. So then it might have some effect.
Okay.
You
Yes, sir. Yes.
denature the protein.
Okay, sir. Yes, sir.
Okay. Any other questions?
Yeah, thank you.
Sir, I have a question.
Yeah.
So, sir, does this delta G value corresponds to one of the minor group that is present in that protein folding funnel?
No, we are talking about from the top to the bottom. We are not talking about minor valleys in protein funnel. So we are talking about thermodynamic minimum to the top of the funnel, delta G.
Okay, sir. Okay, sir.
Okay, so all those minor changes, for example, let's say if the solubility is formed, then you might have a small other valley. And let's say if you have a disulfide is formed and the small valley. We are not really talking about those things. We are talking about thermodynamics. So basically this is coming from all the equilibrium contributions, basically from one end to the other end. We are not really worried about the intermediate steps at this stage.
Okay, sir.
Okay. Okay.
One of them is can this be the reason why protein cycle?
Can this
idea of hydrophobic collapse be the reason why protein cycle?
Yeah, so it could be because that's the first step. Okay, so what we haven't really talked about intermolecular interactions. Okay, so what we discussed about a individual polypeptide chain. Imagine there is no other polypeptide chains, how this collapse. But imagine if each molecule has access to other molecules. Okay, so then this hydrophobic collapse can be combined from different molecules. So hydrophobic groups of different molecules come together, form a cluster. So this you would call a cluster of molecules or the aggregate. It's possible. Okay, and you always have cases where actually this will not fit. For example, let's say if you have a polypeptide chain where you don't have hydrophobic groups, this will not work, right? Okay, so let's say then that might not even have a folded structure. These are soluble, then they might have structures, plethora of structures, so not a unique structure. It's possible. And yes, hydrophobic collapse is one of the ways actually aggregation. Okay, so this is applicable to even membrane formation. Okay, so let's say what happens if you put individual lipid molecules. Okay, so why two lipid molecules come together is because of that methane example. You know, so even if because the solubility is so low, okay, though we call it's not soluble, so all molecules are actually soluble in all solvents, but the thing is that it's very slow. So lipid molecules, when it finds another lipid, the stabilization is so huge, okay, in terms of increasing the decreasing the order of water molecules or side chain interaction. So it's collapsed. And the same thing is applicable for, I would say, peptides or proteins. Intermolecular interactions dictating the collapse, which one can really say a part of aggregations. Okay. What are other questions?
So that was actually two questions.
Hmm.
And the third question is that there are some proteins. So one thing is pretty much clear that while on increasing temperature, the protein are. But when there are some proteins which is stable up to very high temperature.
Yeah.
So in that case, which of the three terms is affected most?
Stable. Okay. So we talked about from the unfolded to folded, but then we have to talk about the opposite as well. Unfolded. So when we say something is stable, we are talking about it's folded, it's stable. Why? Yeah, but why it is not going back to the unfolded? Okay, so that's when actually the barrier will come. Okay, so now if the barrier is very high, so then it will be very slow for the crossing the barrier. Okay, so the kinetics of unfolding is coming to picture. Okay, so that's one way why the process is very slow. But in that sense, then folding is also very slow for them, depending on how the delta G. If the delta G is really large, then the folding might be faster, but the unfolding is very slow. Okay, so it's basically dictated by barrier as well as the overall difference. Yeah.
In case of some proteins, there might be like small mutations in the residue which makes it thermally stable.
Yeah.
So enthalpy contribution is there, I agree.
Yeah.
But are the entropy contributions affected?
Sorry, what?
So there are proteins like let's say the cytoplasm, which in some cases they are like thermally very stable class of cytoplasm. So in such case, I agree that due to few mutations, the enthalpic terms are changing.
Yeah.
But are the entropic terms affected?
Entropic effect, not much, I would say. No. Okay, but the barrier might be different. Okay. Okay. So barrier dictates, for example, a folded protein, how fast it can go back to the unfolded state. Barrier is important, and entropy more or less doesn't really change much. Okay. Okay. So entropy depends on two factors. So what are the conformational flexibility available in the unfolded state, and what is the conformational rigidity available? Okay. So more or less mutations. Okay. In the end, if it takes similar structure, the entropy is not much different, right? But enthalpy is different because this bond is absent now. This bond is absent here, and this bond is absent here. So enthalpy is changing. So this is changing, okay? But these two are mostly not affected. Okay, any other questions? Okay, then we'll conclude.